Dr. Bursten is an assistant professor in the Department of Philosophy at San Francisco State University. She recently completed her doctoral work in the Department of History and Philosophy of Science at the University of Pittsburgh. We're very excited to have her here, and so let's give her a welcome.
Thanks, everyone. Can you all hear me? Okay. If this cuts in or out, let me know. So I'm here today to talk to you about a collaboration that I was involved with for about 4 years during the course of my graduate career with a group of nanoscientists who worked at the University of Pittsburgh. And what I'm going to show is that collaboration is often about getting people on the same page. So that's what we're going to be doing for most of the time here today is, I know we have a mixed crowd of philosophers and scientists and people who think about nano and people who think about other sciences and undergraduates and graduates and a few faculty members here and there. So I've got a little bit of something for everyone. And I'm going to be, well, I guess I'm in the rare position as a philosopher of actually being a practitioner of something more than a theoretician of it. I'm going to be demonstrating to you what we did during our collaboration and showing you in both in the way that the talk is structured and in the content of the scientific research portion, some of the ways in which we collaborated over the course of our grant together. So the talk today is going to come in 4 parts, and for ease of navigation, you can follow along at the bottom throughout the talk. I'm going to be talking a little bit first about historical relations between philosophy and science. How many of us are philosophers in the room? Need a little raise hand, raise pizza. Okay. So this is going to sound a little bit more familiar to you guys. Those of you who didn't raise your hand this time around, we're going to bring you onto our page. Tell you a little bit about how philosophers have thought about science over the course of philosophical history. And then I'm going to give you my view of what we should be doing as philosophers in our relationship with scientists today. No surprise, it's in the title of the talk. I think philosophers and scientists should think of themselves as collaborators, and I'm going to show you in the third section of the talk how collaboration has worked for me over the course of my career so far. Then in the last section of the talk, I'm going to offer some suggestions for developing collaborations. These are suggestions that are pitched partially to philosophers, because as a philosopher, that's where I come from. But they're also ones that will work for scientists and science students thinking about reaching across the aisles in your science collaborations with other departments, with philosophers, with historians, with political scientists. So that's the plan. Let's get started. I told you we're going to start with a little bit of history, and this is how I started thinking about this talk. This is the motivation for structuring what I want to do for the next hour or so. I thought about what relationships between philosophy and science we want to cultivate as we move into the 21st century. In order to think about what relationships we want, we have to figure out what relationships there are, what relationships there have been. So here are 3 that come to us from the history of the relationship between philosophy and science. Philosophy is the handmaid of the sciences, philosophy as the sovereign or master of the sciences, and philosophy is continuous with science. Let's take a look at those in a little bit more detail. So philosophy is the handmaid of the sciences. Those of you who raised your hand said you're philosophers. You may have heard this one before, right? Anyone? Okay, good. Just making sure. I know we're still digesting the pizza, but I just want to make sure that I'm not talking to dead air here. So philosophy is the handmaiden of the sciences. Very famous apocryphal saying in philosophy. A lot of philosophers of science come to philosophy of science thinking that this is what they're going to do. The only problem with this famous apocryphal saying is that no one ever actually said it. It turns out that philosophy is the handmaiden of the sciences comes to us from one of these funny telephone games of scholarly history that has changed the way that we understand 2 very different sayings that came to us both from the early modern period in history. During the early modern period, we were getting the beginnings of what we call the scientific revolution. Scientific revolution was where we start to see investigations of the natural world systematized. It's where we see the birth of what we call science, what we do when we walk into labs today. For most of this period, people who were doing what we would call science today, what we identify as science, would call themselves natural philosophers. Natural philosophers, people who are investigating the natural world, looking for explanations not in terms of myth or magic or religion, but in terms of natural phenomena, right? Those of you who are scientists, is that what you do? Yeah, more or less. One guy. That's what one guy in here does. Everyone else, you're not sure what you're doing yet, right? Okay. So we have the scientific revolution. We have one thing that sounds a little bit like philosophy is the handmaiden of the sciences. It comes to us from John Locke, famous philosopher, natural philosopher, who says it's the ambition enough to be employed as an underlaborer in clearing the ground a little and removing the rubbish that lies in the way of knowledge. So this doesn't actually say philosophy or science in it. But you can see that what he's trying to say, and he's talking about philosophers here, the ambition enough of philosophy, is that he's trying to say philosophers, we're like the janitorial staff of knowledge. We're trying to figure out how to clean it up, how to make it a little bit prettier, a little bit more understandable, a little bit more systematized. But that's all we need to do as philosophers. That's our goal. There's a very different saying that's become part of our philosophy as the handmaiden of the sciences view, which comes to us from the originator of the modern scientific method, Francis Bacon. He says, knowledge is the handmaiden of power. That's a very different claim than philosophy is the handmaiden of the sciences, but that's the only historical evidence of the handmaiden analogy that we actually find from the early modern period. So that's our philosophy as science's handmaiden view. A little bit of a sketchy historical approach to it, but it's one of the main views that is out there today. It's one of the main views that some philosophers of science still see themselves as doing. What are you doing as a philosopher of science? Well, you're looking at scientific theories as they're presented to you. You're cleaning them up. You're making them connect more clearly with other areas of science, with other areas of human knowledge. So you could ask questions about whether or not consciousness can be reduced to electrical signals in the brain as a philosopher. And you're taking evidence, taking data from neuroscience, from cognitive science, from psychology, and you're connecting it to classical philosophical questions about the nature of mind and the conscious experience. And you're just trying to clear away all of the rubbish. Right? We'll call them the epistemic janitors. So that's one view. Here's a very different view coming to us from David Hume, another empiricist writing a little bit later than Locke, but in the same era. He says, "'Tis certainly a kind of indignity to philosophy, whose sovereign authority ought to be everywhere acknowledged, to oblige her on every occasion to make apologies for her conclusions, and justify herself to every particular art and science, which may be offended at her. This puts one in mind of a king arraigned for high treason against his subjects." Hume is not okay with being a janitor, right? So again, we're talking in the 1700s. The view of what counts as art, what counts as philosophy, what counts as science, those words mean something slightly different at that time period than they do today. And that's going to be something that we come back to over the course of this talk, how words mean different things in different contexts. But what Hume is trying to say here is that philosophy's role is the master, the sovereign, the watchdog. The 20th century takes this view of philosophy's relationship to science and turns it into philosophy as the watchdog of the sciences. We're trying to make sure that the sciences don't overstep their boundaries, that they don't make claims that are broader than we think they should be, that they stay within ethical boundaries, that they connect their theories to other scientific theories in appropriate ways. We are the ones who understand what knowledge is better than the scientists. So we are the ones who are going to come in and tell the scientists how to structure their theories. Scientists, you can give us the evidence, but philosophers, we're the ones who are going to tell you what that evidence really means for the nature of human knowledge. How happy are you scientists with that one? Okay, I got one thumbs down. Everyone else is still eating. Got a fight brewing right there. Okay, so we have the handmaiden. Philosophers are the janitors. We have the sovereign. Philosophers are the masters, the watchdogs, the ones putting science in its place. Neither of these are great for both philosophers and scientists. So along comes, in the 20th century now, a guy named Willard Van Orman Quine. And he gives us a very different view of the relationship between philosophy and science. He says, my position is naturalistic. I see philosophy not as an a priori propedeutic or groundwork for science, but as continuous with science. So here, notice that this view he's arguing against in the very first bit is the sovereign authority view. He's saying that one, not going to work for us. Instead, I see philosophy as continuous with science. I see philosophy and science as in the same boat, a boat which, to revert to Neurath's figure, as I so often do, we can rebuild only at sea while staying afloat in it. There's no external vantage point, no first philosophy. Philosophy and science, basically the same thing. Everyone cares about knowledge. Let's just all call our differences differences of degree, not differences of kind. Fair enough. So we've looked at 3 historical relationships between philosophy and science. I want to show you that there are some problems with each of them. We've seen a few problems with the first 2 views already. Philosophy, as the handmaid of the sciences, isn't actually historically accurate. That's a problem if you care about history, which I do, and which if you do philosophy of science, you should. If you do science, you should. You should care about history, period. But in case you don't already care about history, let me just tell you it's not historically accurate, and that should matter if you care about history. It doesn't leave a whole lot of room for philosophical innovation. If philosophers are the epistemic janitors running around cleaning up after the scientists, they're not going to be making a whole lot of new philosophy themselves. They're just going to be saying what's better or worse about one scientific view. They're going to be clearing the rubbish, the lies in the way of knowledge, right? Which is a humble ambition, and of course, there are such things as false humility, which philosophers are excellent at practicing. But I think Locke did actually mean it in this genuinely humble way. And that's fine and well and good, but if you're a philosopher in the 21st century and you think, I actually might have something to contribute, it doesn't leave you a whole lot of room, a whole lot of places to go. It's also a little bit hard to implement. The way that scientific research has evolved in the 20th and 21st centuries has exploded the number of research papers out there. So if you think about really, put ourselves in our janitor mode, trying to clean up scientific papers as a whole, read all of them, figure out what's true in all of them, and what could be left behind in all of them. If you try and Google Scholar Search just articles published in 2016, well into the millions, and we're only in March, right? Philosophy is the sovereign of sciences. Well, that one forges a little bit of hostility. We already saw a little fight break out in the 3rd row here. It's also not a particularly useful description for philosophers who want to engage with scientists themselves. It puts philosophy in a very different corner than the sciences, and it gives them both very distinct sorts of roles in any relationship that we might develop between them. It's also a little bit hard to implement because, I don't know if you guys know, but philosophers are not sitting around chairing all of your scientific departments right now. We're not actually in a position to tell you what to do. So it's not clear why we want to hold on to that view at all. The more promising view, the view from Quine that says philosophy and science are a difference of degree, but not in kind, is a gentler approach to the relationship between philosophy and science, and it's one that starts to get at an idea of a productive relationship that we could establish between the two. But it overlooks, with some significant differences, both in methodology and the way we solve problems, and in expertise, what we're good at. I cannot operate a transmission electron microscope, but I can tell you about all of the differences between TEMs, SEMs, AFMs in a taxonomic structure of microscopes that I could build in my brain, which not a lot of scientists sit around spending their spare time doing. Philosophy is very good at teaching you a certain kind of problem solving, a certain kind of rational approach to organizing phenomena that science sometimes requires of you in certain branches, but which isn't the focus of a lot of scientific research. We also run into similar implementability problems that we had with the first two views, in that, well, philosophers certainly can't get paid like scientists. We'll put it that way. Okay, so we've looked at a few relationships that have existed or have been proposed between philosophy and science over the course of our early modern to contemporary history. And I want to propose the view that I think is more realistic and more promising now. I think philosophy should be considering itself as a collaborator of the sciences. Philosophy and science use distinct methodologies, but they can collaborate effectively and contribute effectively to each other's research in areas where they overlap. Then it just becomes a matter of finding those areas and figuring out how to talk about them, how to get everyone on the same page. So what this allows us to do is abandon the metaphors, the handmaiden, the sovereign, and instead study instances of successful collaboration for insight into how we should think about what collaboration between philosophy and science can look like. I think this paints a relationship between philosophy of science and science that is mutually beneficial, that's constructive, that allows it to evolve over time in response to the genuine challenges that face both philosophy and science today. All well and good. Collaboration isn't where we stop. It isn't the end of our story. It's really the beginning. And luckily, there are scholars out there, humanists, scientists, who study the dynamics of collaboration itself. So we can think of collaboration as a jumping off point for understanding and looking for new ways of engaging across the aisles. So we'll take a quote from Peter Gallison, a historian of science who's working at Harvard these days. He says, instead of ending an analysis by reference to a symbiosis or collaboration between scientific and extra-scientific subcultures, I want to be able to ask, what are the dynamics of the interaction? This is Gallison writing a reflection on a book that he wrote where he did ask exactly that question and where he came up with a set of answers that we'll see in just a second. Before we get there, though, I want to give you just a list. This is not an argument for a particular view, but this is a list of features of collaboration that I've run into in the course of my collaborations. One is feedback. My research is deeply informed by the specific lab that I work with, the specific sorts of problems that they study. Their research is specifically informed by the way that I think about philosophy. You've heard the way I think about philosophy. I think that history is important. I think that there is a lot of ability to come together around the particular words that we use. And you'll see that those come up over and over as I start to describe the individual instances of collaboration that my lab and I had. So there's room for pluralism. What do I mean by pluralism? I mean that different methods work for different people, that there is not one universal law that's governing all interactions that says, before I can talk to a scientist, I must fill out 7 release forms and present a proposal and develop a grant. Sometimes I have to do that to get access to very particular sorts of scientists. Usually not. But it also gives us room for differences in interests. I can ask questions that might not be particularly interesting to the scientists. If they're feeling generous, they'll sit around and answer them. If not, we don't tend to collaborate together. They can ask questions of me that may be pedagogical, may be research-oriented, maybe questions for vocabulary, maybe questions for history of their own fields. A lot of scientists don't get formal education in the history of their fields. And sometimes these questions are going to be interesting to both of us. Sometimes they're going to be interesting to one of us, and that's okay. That's part of the story. Collaboration works well when it is mutually beneficial, but that doesn't mean everyone has to get something out of every instance of an interaction. So room for awareness of differences in interests, differences in goals, differences in backgrounds, without that becoming a point of contention, right? So this is why that philosophy as continuous with science view doesn't quite hold up for us. It also fosters a dynamic of peerhood, which means that we get to treat each other like people, right? Equitable engagement across the aisles, respectful communities, productive discussion, all of those nice things that you probably heard in diversity workshops, where it's just nice to be nice to people instead of calling them your handmaiden or your master. And we get a corollary out of this dynamics of collaboration by calling philosophy and science's relationship a collaborative one. That means that we can use theories of interdisciplinarity, which are already out there. There are scientists who are studying how do biologists and physicists work together to create nanobiostructures. How do physicians and anthropologists work together to study the way that medicine is introduced into new cultures, right? We can take those theories of interdisciplinarity that already exist in order to understand our relationship to science, in order to understand how philosophy and science should get along. So let's do that right now. I showed you Peter Gallison a little earlier, and I told you that he thinks collaboration is the beginning of the story, not the end. And the end of the story for Gallison is a deep analogy to something that he calls trading zones. He has a trading zone theory of interdisciplinarity, where he says that when I am getting together in an interdisciplinary effort, as a philosopher or as a scientist, talking to a scientist, what I'm doing is creating a zone of exchange, a borderland where I share some vocabulary, share some concepts, share some methods maybe. And through that borderland, where I can exchange things, he develops an extended economic metaphor to cultures coming together. They might not share a language, they might not share a religion, they might not share a culture, but they can get together and trade with one another. That's where we get the trading zones metaphor. So there are going to be shared words for economically interesting things, like money and goods and services. There might not be shared words in economic trading zones for things like, I don't know, family relationships, dinner time. Those might be things that are shared individually within the cultures, not across cultures. I think that's a really good start, saying that the way that we start collaborations is by finding a little bit of common ground and building a language around it. I'm going to show you in the next section why I think that's not enough, especially for extended collaborations. But it's a good start. Collins and Evans, a little bit after Gallison writes his trading zone theory, build out a notion of interactional expertise, which takes the transactional, the economic understanding of trading zones and develops it even further to say it's not just a transaction, it's an interaction. It's something that happens over time. It's something that happens via exchanges. They get even more complicated in their economic metaphors, and I assume that not a ton of us in here are economists. That's the one. So I'll leave it at that for now. So these give us a very transactional, interactional, exchange-based idea of what's happening in a collaboration or in an interdisciplinary effort, which is a good starting point. But I think it overlooks something that can happen in long-term collaborations, which is that we construct things over time. Not only do we do we exchange, we build. And I'm going to show you in the next section some of the ways that we've built up new theories, new concepts in our collaboration with the nanoscientists at the University of Pittsburgh. I just want to highlight one more thing here because, again, I like my history. Cyrus Modi is a historian of nanoscience. He talks about the development of scanning tunneling microscopes in the 60s and again in the 80s, and how those communities formed around their ability to use certain instruments. People from different backgrounds came together, physicists, engineers, chemists, biologists. They talked to other people who were using the same microscopes as them, rather than other people in their department, in their university, rather than other people who were working on the same substances or the same applications. And those communities of instruments really drove the way that nanoscience research in particular has evolved over time. So I think that gets at the constructive aspect of collaboration in nanoscience. But it's not really clear how to project that notion of instrumental gathering into interactions between scientists and non-scientists, in particular between scientists and philosophers. Like I said, I don't know how to work a TEM. I don't know what the equivalent thing to one of those microscopes is that we can put on a table and share with each other. So if you're interested in the history of nanoscience, if you're interested in this idea of dynamics of collaboration, I really recommend going out. The book is actually called the same thing, Instrumental Community. It's a really nice way of starting to think about how interdisciplinarity has shaped the history of nanoscience already. Okay. So I've said a lot of things about what I think collaboration is and why we should have collaboration between scientists and philosophers. Now I need to show you what you get if you actually do it. Here's my group. The Millstone group at the University of Pittsburgh. Our PI is Jill Millstone. She is here explaining science to people. You can tell because her hands are big. So our group is a group of nanochemists at the University of Pittsburgh within the chemistry department with joint appointments in mechanical engineering and materials science, physics, and the Pittsburgh Quantum Institute. We study colloidal metal nanosynthesis. So we are making nanoparticles using chemistry rather than physics. Those nanoparticles are usually very small. And shaped rather like geometric shapes than wires or thin films. If you look at nanoscience, you can separate it out in a few different ways. I've told you as a philosopher I like classifying things into different categories. One way you can think about it is the people who do metal and the people who do carbon, or the people who do metal. Another way you can think about it is the people who do thin films, the people who do wires, which we call one-dimensional nano objects, and then people who do small geometric objects like these triangular prisms, these little rods. We also make cubes and lumps. We try not to make lumps because it turns out lumps are not the most interesting things to study. But we make small geometric objects as opposed to long wires or films. You can also separate out nanoscience in terms of what materials are being used, what elements these nanoparticles are being built out of. So not only do we look at metals, we look at noble metals. Gold is one of the canonical metals that you use in nanosynthesis. And we look at gold, we look at platinum, we look at rhodium and a couple other less common noble metals. What the group is interested in is the very basic question of what is the relationship between nanoscale structure and nanoscale properties and behaviors. For those of you who don't live in nano worlds, who don't study nanoscience or work in nanoscience, what's exciting about nanoscience is that very common materials behave in very strange ways when you shrink them down. So for instance, this little vial that looks like cranberry juice is actually very small, finely divided gold particles. Very small, finely divided gold particles don't look like the common yellow gold that we are used to. They turn red. Very small, finely divided particles of silver turn blue. That's actually where medieval scholars and, sorry, not scholars, craftsmen, got the color for their stained glass by mixing very finely divided metal powders into the glass as it was melting. So that's one example of a difference in properties that we see between the nanoscale and what we would call the bulk scale or the macroscopic scale. And in the Millstone group, we look at the controlled chemical synthesis of nanomaterials that leads to the development of structure-property relationships, relationships between the shapes of our materials, the surface chemistry of our materials, the chemical compositional identity of our materials, and the properties that they exhibit. Color, but also electronic properties, also catalytic properties, also plasmonic properties. Which can then be manipulated into a whole host of applications in everything from electrical engineering to medicine. So the Millstone group works to develop new tools and new insights for nanoparticle synthesis that allow us to access nanostructures that incorporate optical, electronic, mechanical, and self-assembly demands into a single nanoparticle architecture. No big deal, right? No, it's a very noble, very high goal to be able to incorporate into one structure all of these different properties and the ability to tune and exhibit all of those properties in exactly the way you want them to do. That's the sort of holy grail of nanosynthesis. So where do I come in? Well, here's our group poster from a couple years ago. You can see we are working on surface chemistry and the ways that surfaces are going to affect the overall properties of the material. We're working on absorption of alloys into nanoclusters. So mixing a second kind of metal into a single metal nanoparticle. We'll see that again later. Using the surface chemistry to tune the optical properties. And we also have the conceptual foundations of nanoscience. And I know it's very small, so we'll zoom it in a little bit. What we're doing in the group is investigating the philosophical underpinnings and theoretical frameworks that we use to understand material behavior at the nanoscale. I gave you an example, the way that we classify and partition out what nanomaterials are. That's something that our group actually worked up together over time. It's a fairly common classification system that's out in nanoscience today, but it's one that's not generally accepted full stop. It's not like the F equals ma or the periodic table of nanoscience. It's not codified out there forever in the way that we think those other laws of nature and classification systems are. Nanoscience is very young, very experimentally driven. If you have to write grants for your research, you know that one of the ways that you get grants is by saying, I'm going to do one experiment that has one revolutionary application. People don't give you grants for saying, I'm going to investigate the theory of nanoscience and give you better laws of nature or relationships among the phenomena at the nanoscale. So that's what we do kind of in our spare time in our collaboration. So I have a couple examples down here. One of the ways that we think about nanomaterials is whether or not the proper description of a surface in a nanoparticle system is atomistic, if we think of the surface atoms as existing individually with individualized properties, or whether it's continuous, and we get things like surface curvature and surface energy. We show how the differences between those ways of conceiving of nanoparticles affect the way that we ask research questions differently. And we'll come back to that as we go through this section. So before we do that, I just want to get you a little bit caught up on what is so exciting and so different about surfaces in nanoscience. At the bulk scale, normal materials like my laser pointer, my jacket, even my hair, individual strands of hair, effectively none of the atoms in those materials are on the surface. Even down to my hair, which is much larger in diameter than the 63 micrometers listed here. Most of the atoms in that material, that strand of hair, are on the inside of the material. So what the surface is doing doesn't really affect what the overall material is doing. Zoom down to the nanoscale, zoom all the way past the nanoscale to molecular materials. Things like, does anyone know what this molecule is? Any chemists in the room? Something that we all could use right now? It's caffeine. So in our caffeine molecule, it doesn't really make sense to call any part of that material the surface of the material, right? There's no real boundary between the outside and the inside in the individual rings or in the individual atoms. At the nanoscale, we hit this interesting in-between region where there still is a surface. There's a surface that's part of the material. The outer layer of atoms is some, but not all of the material. But the surface behaves very differently than macroscopic surfaces do. And it has a very different impact on the overall structure and behavior of the system. So nanoscale surfaces are not infinitesimal in the way that we think of macroscopic surfaces as being effectively infinitesimal. It's the surfaces of nanomaterials that give rise to a lot of these interesting differences in properties that I was mentioning before. So the reason that those gold particles are red is because of behaviors on the surface of the material. It's also the case that surfaces in all materials are less stable than the interior of the material. As a result, surfaces are higher energy. When effectively none of your atoms are on the surface, that fact doesn't make a big difference to the way that you treat the system. When 35 or 45 or 85% of your atoms are on that surface, you got to do something about that surface to hold it together. So nanomaterial surfaces require stabilization in a way that macroscopic material surfaces don't. I don't have to wrap my gold ring in any sort of chemical or physical coating in order to make sure that that gold ring doesn't turn back into a lump of gold. I do have to wrap my gold nanoparticles in a casing of chemical surfactant in order to make sure that they don't agglomerate back into a lump of gold in that vial. So the change in surface behavior and surface structure leads to changes in the way that we think about surfaces. What the surfaces are, what they're doing for the material. We model surfaces differently at the nanoscale than we do at the macro scale. We can't use normal continuum descriptions of surfaces in nanoscience in the same way that we would use them for modeling bulk materials. That in turn leads to changes in the way that we think about the synthetic and electronic and mechanical properties of nanomaterials. In philosophical terms, we attribute the causal power of surfaces a lot more weight in nanomaterials than we do in macroscopic materials. We say that things are happening to nanomaterials because of the surface in a way that we wouldn't say that they're happening to macroscopic materials because of the surface. Surfaces are a different concept at the nanoscale than they are at the macro scale. This is where we start to see a little bit of conceptual analysis being performed on the idea of a surface itself as it shows up in nanoscience. Another example of differences between the way we think about central concepts in nanoscience versus macromaterial science is in the idea of an alloy. So one of the things my group does is try and make alloys at the nanoscale. We try and mix those gold nanoparticles with individual atoms or 4 or 5 atoms of copper, or what else are we using these days? Cobalt. Into our gold particles to see what happens. And it turns out that if you add individual atoms like that to very, very small materials, you can get wide changes in properties with a single atom difference. You can't get that at the macro scale. So alloys in general, in macromaterials and nanomaterials and any material, What we call an alloy is a mixture of two metals, two or more metals, or of one metal and one nonmetal. So for instance, steel is an alloy even though carbon is not a metal. Just a little sanity check. Steel is made of carbon and iron. Okay. Alloys can be disordered, like this top one, or they can be something called intermetallics, where you actually have crystalline structure, regular repeating structure of one, we call it a heteroatom, or a secondary alloy metal, embedded into the structure of the initial metal. At the macro scale, you don't see intermetallic structures. You don't see regular repeating unit cells of alloys in the same way that is pictured here. And at the nanoscale, these two different arrangements have different properties. I told you that what we're interested in nanoscience is getting the relationship between structure and property. And these are two different structures, in part because they give us different properties. If this arrangement gave us exactly the same set of properties as this arrangement, we might not even bother to call them different structures in the first place. Conceptual analysis. What does it mean to be an alloy? So one of the questions that we've been asking lately in the group, and I was just in Pittsburgh this weekend asking this question with the graduate students, why are we thinking of alloys in the same way? Why are we calling these multimetallic mixtures of metals alloys at all? What do we get by calling them alloys that we wouldn't get by just saying this is a brand new kind of matter in nanoscience? It hasn't existed before. It's true, this individual kind of matter hasn't existed before. We're making it for the first time. Why do we want to call it by the familiar old term? What are we getting from that? Well, we're getting the ability to think about what alloys do. In macroscopic materials, alloys mix in a whole bunch of different ways. And the way that they mix, the size and the distribution of different metals within an alloy is called grain structure, grain behavior. Grains in macroscopic alloys can be 200 or 300 nanometers in length easily. The materials that we're making, the entire material is about 2 nanometers. So we certainly couldn't have a 200 nanometer grain of one metal within a 2 nanometer cluster, right? That's how numbers work, okay? So we have a very different set of constraints on where we can look for the relevant structure in these alloys, in nanomaterials, than in macroscopic materials. But one of the things that we do in macroscopic materials is think about the relationship between surface alloying behavior and interior or bulk alloying behavior. So in macroscopic materials, we see, for instance, strong mixing between gold and copper. You can make a gold-copper alloy very easily at the macroscopic scale. But the surface of that alloy is going to exhibit a lot of, is going to exhibit much less mixing. It's going to exhibit a preference for one of the metals migrating inside of the other metal in a way that in the bulk you don't see. You don't see this separation all the way out into a structure where you have one metal wrapped around the other. You see strong mixing at the macro scale, but strong migration at the surfaces. So there's an open research question out there for nanoscientists. Do our gold-copper alloys behave like our bulk behavior, or do they behave like our surface behavior? Are we going to have migration of one metal into the other, or are we going to have strong incorporation all around? Well, we asked that question, and we answered it. It turns out that if left to their own devices, we get behavior like we would see in the surface migration patterns. But it is possible to both model in a computer simulation and to actually constrain the way that we make the materials such that we can get bulk-like mixing behavior where you get atoms of the second metal scattered throughout the first metal. And in nanosynthesis, it's path dependent. It depends on how you set up the synthesis, how you grow the seed crystals over time, how you make the material is going to determine whether or not you have a bulk-like or a surface-like alloying pattern. That's something new that we learned as scientists by asking the question, what are the analogies that we have between bulk-like alloys and surface-like alloys and our nanomaterials? So our metal mixing behavior in nanomaterials varies greatly from the normal bulk because we don't get large islands of one metal or another. We get similar differences in properties based on the location and the distribution of the second metal in the first metal. So there are reasons that we want to keep this notion of an alloy around, even though what we're doing in nanoscience is mostly making a set of analogies to macro scale or bulk scale alloys. We're saying that the grain structure in bulk scale alloys is like the individual atoms in nanoscale alloys. The behavior of the nanoscale metal mixing is like bulk scale mixing in some ways and like surface scale mixing in other ways. And we can tell you a story about the differences between them. So we're keeping the idea of an alloy around in part because we want to make analogies between bulk scale behavior and nanoscale behavior. Why? Because a lot of our students started with macroscopic or bulk scale metals, because there are a lot of models out there that tell us about the behavior of bulk scale metal mixing. There are a lot of theories of metal mixing, and there are a lot of applications for metal mixing that we might want to draw on later on in research. If we throw out the idea of an alloy, we lose a lot of ability to explain what we're doing in our lab and to look for new ways of understanding the patterns of structure and behavior that we're seeing correlated at the nanoscale. Thank you. Okay, I asked Lacey to give me a little hand wave when I was getting about 15 minutes out. So I'm gonna skip my last case here, but we can come back to it in questions. Instead, I'm going to talk a little bit about what I call the epistemological implications of the cases that we've seen so far. And this is where I start doing my own philosophical research. This is the research that I did in my dissertation. I looked at the idea of scale dependence. What I mean by that is that when we do conceptual analysis on concepts like surface and like alloy, what we see is that surface means something different at the nanoscale than it means at the bulk scale. Alloy means something different at the nanoscale than it means at the bulk scale. What those differences show is that we use different models, we use different theories, we make sense of these concepts differently, both as scientists and as philosophers. Now, there's a common set of questions that you can ask as a philosopher. Does one science reduce to another science? Can we explain all of nanoscience in terms of continuum mechanics? Can we explain all of nanoscience in terms of molecular mechanics? And what I try and show in my dissertation that the answer is no. We can't use just one or just the other. Nanoscience is not going to reduce to either of these other sciences because it draws on resources from both in order to explain the behavior of the materials that it's making. So what I call that instead is conceptual scale dependence. And that's something that our group has been working on explaining both to philosophers and to scientists. This is an instance of a philosophical view out there called conceptual extension, which says that we have common concepts that may not apply in new or strange domains, such as the concept of weight when we're in space. If you ask someone how much they weigh and they're floating around on a spaceship, well, we know technically they just have mass and not weight at that point. But an astronaut sitting on a spaceship may say, well, I weigh 160 pounds when I left. I'll probably weigh 155 pounds when I get back. It's not that all of my weight disappeared then. It's that the concept needed to be extended to make sense of what was going on in space, right? So I showed that moving between bulk and nanoscale concepts of surface and alloy requires extending our common concepts into new domains. If you don't like the weight example, you can think of another one. We take the example of hardness. In material science, there's a lot of tests for hardness. You can scratch something, you can bend it, you can deform it, you can tap it. All of those different tests are going to reveal a different dimension to what it means to be hard. The bendability tests reveal certain kinds of elasticity or resistance to deformation, which require a certain amount of non-rigidity in the crystal structure. Scratching or tapping is going to require a different amount of rigidity in the crystal structure in order to explain. When we move our concept of hardness from bending to tapping or scratching, we end up in new conceptual domains. So what I show is that when we move from the bulk and nanoscale concepts of surface and alloy, what we're doing is moving to new conceptual domains and making the choices to keep or discard certain sorts of associations. We keep the association between different metals, different properties. We abandon the association between different grain structures, different properties, because we don't have an analogy to distribution of grains or structure of grains in the nanoscale. Let me rephrase that. We have an analogy to distribution of grains. We don't have an analogy to grain structure, because what is affecting properties at the nanoscale is individual atoms, not grains with different shapes and structures. Okay. So we make choices to keep or discard these associations, these analogies. And all of this shows us that these traditional philosophical questions, whether or not one theory reduces to another one, can be answered by non-reductive and what's called non-emergent approaches to intertheory relations. I'll be happy to explain that in the Q&A if you guys are interested. That's more of a flag for the philosophers. Okay, so this is a cool example of conceptual analysis in practice in our lab that I will be happy to go through in Q&A. We're going to have to watch through the animation real quick here. Okay, so the upshots of this collaboration are some for scientists, some for philosophers, some for both. And as I said earlier, one of the reasons that I don't like the idea of philosophy and science being continuous with one another is that different parties are going to benefit at different times in different ways by using different methods. And if you take the continuity relationship between philosophy and science, you can't explain how those differences still lend themselves to a successful collaboration. So in the nanoscientists from this collaboration get a new set of laboratory tools, namely conceptual analysis. I get new native research questions. This idea of what a surface means at the nanoscale came from discussions with the nanoscientists. It didn't come from sitting back and reading philosophy. Another thing the nanoscientists get, cheaper solutions to problems. So this one, I skipped the example of the nanomechanics application, but we solved an experimental problem that one of our grad students was having by rethinking the problem rather than redesigning the synthesis or by repeating the synthesis over and over again, which costs time and effort and materials costs. I also get a constant check on my understanding of what the scientific method is. One of the questions philosophers of science ask is, what is the scientific method? What is the structure of theories? If you're the sovereign authority of science, you can ask that question without ever consulting scientists. But that just means that the sovereign authority model is a bad model for the relationship between philosophy and science. If we're trying to do responsible, descriptive philosophy of science, saying what the human activity that we call science really is, we'd better be engaged with what the scientists themselves are doing in order to create those descriptive accounts. There are a couple things we all get, right? We get practice explaining research outside of a narrow group of experts, which is both instrumentally useful for things like getting jobs, but also inherently useful. You tell stories differently to your roommates and your friends than you tell to your PI or your chair or your dissertation supervisor. You explain your research differently when you're talking to scientists than when you're talking to philosophers. And that means both philosophers and scientists are going to explain their research differently in different groups. And that gives us a more robust understanding of what it is that we're doing. Explaining our research in those different ways can often lead to new insights as you're talking, as you're collaborating, to find new areas of overlap, of domain extension. Okay, I think that's all I'm going to say about that one. You also get claims to interdisciplinarity. Genuine interdisciplinarity, which means you can use theories of interdisciplinarity to make sense of it, and you can collaborate. You also get to claim interdisciplinarity on grants, which is very nice, very hot these days, especially in research parks like this one, which are all about interdisciplinarity, both on paper and in practice. Okay, some of the benefits. In my last few minutes, I want to offer a few suggestions for how to think about seeking this sort of collaboration yourself. So I've told you a few, getting some weird feedback, right? Maybe if I pull this out. Do you know why I'm getting this?
It's only when it's quiet, it has a noise canceling function.
Oh, so I just have to keep talking the whole time. Okay, not a problem. This is like, what is that? One of those improv games, right? Just never stop. So I told you about some of the collaborations that my group and I worked on around the ideas of surfaces and alloys. But we did a lot of other things together too. So here are a few examples. As I was working with them in Pittsburgh, I came in and gave introductions to my research, introductions to philosophy of science, the way that I did in the first section of this talk. And I told them about my dissertation, how I was using their work in my dissertation. I got their feedback. I did an introduction to something called nanoethics for them. This is a bioethics talk series. In addition to there being bioethics, there are ethics of other sciences. Nanoethics is one of those sciences. Nanoethics, it turns out, is not that interesting on its own. There aren't that many problems that you can ask of nanoethics that you can't ask of, say, GMOs. There aren't that many native problems around the structure of nanomaterials that makes ethical questions about them interesting in a way that general scientific ethics questions aren't. Introductions to philosophy of science, as I said. We did a cross-lab discussion group with a group of mechanical engineers that I had found to talk about the way that they simulated thermal transport in nanomaterials, the sorts of nanomaterials that we were making, but not simulating transport in. So fostering interdisciplinarity among the scientists as well. We did an empirical survey of hypothesis-driven science and whether or not the students are genuinely forming hypotheses as they're setting out research projects. We constructed narratives for grants, so I would sit down with some of the graduate students who had never written a grant before and ask them, what is the story that your scientific project is telling? Philosophers, it turns out, are fairly good at identifying broader impacts and narratives of research because we're good at generalizing, we're good at classifying, we're good at that sort of problem solving. We invited the PI of the group, Jill Millstone, to speak at some philosophy workshops. We created something called the Nanosynthesis Wiki, which is an endeavor to make nanoscience research more accessible to underserved communities by offering basic protocols that you can do without a whole lot of fancy equipment. And these conceptual solutions to experimental problems that I've told you a little bit about here today. So let's just run down the list. Some of these worked better than others. The introduction to my research went okay. It turns out that as a philosopher, I have to work to make philosophy interesting to scientists. If they had been interested in philosophy, they would have gone into philosophy. The introduction to nanoethics did not work because nanoethics is not a particularly interesting field unto itself. A lot of our graduate students and postdocs had run into basic scientific ethics questions. We all decided together that we couldn't see anything beyond those basic scientific ethics questions in the nanoethics papers we were reading. The introduction to philosophy of science went okay. Those students who were interested in history, interested in philosophy, liked it, asked for more. The ones who were not did a good job of deciding that they wanted to go into science instead of philosophy. Our cross-lab discussion group went okay. Again, there were individual points of contact. It was a forum where we could create further one-on-one or one-on-three types of collaborations, but in the group setting, it just worked better for some people than for others. The hypothesis-driven science survey did not work well because it turns out that I am a philosopher, not a social scientist, and I did a bad job of designing the survey. I got some interesting answers to questions, but I took it to a social scientist friend of mine for analysis, and she told me that I should have come to her well before I sent out the survey. It wasn't anything worth generalizing over. So know your own methodology. Constructing narratives for grants worked really well. Sitting down one-on-one with graduate students and asking them what they thought their research was doing beyond just answering individual data-driven questions helped both of us understand what the impact of their research was better. Inviting our PI to speak at philosophy workshops went over very well. The nanosynthesis wiki is still a bit up in the air. It's still a project that's ongoing. We're trying to figure out how to release it and publicize it. We're not sure if it's going to work. And our conceptual solutions worked very well. This is the one that I think is the best way of generalizing and thinking about why we might want to collaborate with scientists as philosophers, why scientists might want to collaborate with us, and how to go about doing it. Looking for questions like, what's a surface, what's an alloy, how do we export those bulk scale ideas into the nanoscale? So I want to offer some suggestions to the philosophers in the room for how to go about creating collaborations for yourself. Step one, listen. Listen to the way that scientists are talking about their research. Listen to what they're saying, to what they are confident in, what they're less confident in, what is exciting to them about the research they're doing, what is just a normal everyday part of their research experience. Those are the things that you can get from talking to scientists that you can't get from reading papers. Once you're listening, identify interpretive issues. So when it's hard to talk about what an experiment is, when it's hard for a student to explain to you what an experiment is doing or why they're doing it, that's usually an indication that it's a place to probe further, to draw out more investigation on the vocabulary they're using, on the concepts they're using to explain what it is that they're doing. Now, it may be that this is a difference in background that just means you guys need to build a bigger trading zone among you. You might have to end up learning some math or some chemistry. But it might be a conceptual problem, and the only way you'll know is by probing long enough to find out. And then it's a matter of trying to figure out how to communicate with scientists as individuals. You can think about it like a teaching opportunity. It works better if you can show why the conceptual analysis approach is going to work for the scientists, not just for you, the philosopher. You can draw on examples from the history of science, as I do. And with any luck, the hard things, the things that are hard to talk about, the things that you guys are having trouble communicating about, will lead to conceptual insights that can generalize over time. So I gave a couple examples here. The malleability of space and time and relativity is a historical case of there being conceptual problems with the ideas of space and time in that theory. That led to new mathematical insights, new interpretive insights that we're still making sense of today, as well as the exportation of concepts like surface and alloy into nanoscale research. Here's some things that I didn't do right the first time around, things that I learned from. It is a mistake to think that philosophy is intrinsically interesting to scientists. If you start with, okay, I have this problem in Batterman's theory of explanation, and I want to tell you about all of the history of theories of explanation in philosophy that have led up to that problem, you are going to get glazed eyes even quicker than I just did right now, right? All of the scientists in the room are just like, what is happening? Thinking the same approach is going to work for everyone. Thinking that the way that you talk to your advisor, the way that you engage with your peers is the same way that scientists engage with their peers. So this is one very practical piece of advice for philosophers in the room. We write long emails because that is what we do. We are word people. We write paragraphs to each other. Sometimes we write 10 or 12 paragraphs to each other as part of a normal email exchange. Scientists do not do that. If you send them an email that is longer than 5 sentences, you will never get a response to that email. Some sciences even have norms of exchange where they will bold certain parts of their email or use bullet points to emphasize what they want out of that email. And it's just worth knowing that that's out there if you try to reach out to scientists. And it's worth knowing for the scientists that if a philosopher writes to you with an 18-paragraph email where each paragraph is 6 to 10 sentences long, that's just how they talk. And you need to ask them to talk differently so you can understand them. Another mistake, trying to be anything besides a philosopher of science. When I tried to be a sociologist, it didn't work. Okay, a couple additional practical tips for approaching scientists, and I think scientists, you could take this if you're thinking about approaching someone in a different discipline or if you want to reach out to humanists. Know why you're approaching the particular person you are as opposed to anyone else in the department, anyone else in the lab, anyone else in the university. You want to try and make your job hard but not impossible, right? You want to look for people who might be receptive. You'll find out who's going to be receptive often by getting other people who are receptive to tell you. Humanists and scientists that have undergraduate connections to the humanities, graduate connections to the humanities in some cases, tend to be more receptive to humanistic methodology. It's going to be a matter of trial and error a lot. I did a lot of trial and error before I found my group. I tried to work with 4 other groups. One of them let me in once and then told me that I wasn't invited back because I wasn't making valuable contributions in that first meeting. So yeah, that's all the way down here, but expect rejection, expect feigned interest, expect a complete lack of response, send emails expecting that you're never going to hear back. Make those emails short though when you send them. And practice describing your research in a way that makes it understandable to scientists, which means not starting with in the history of philosophy, there have been different camps such as rationalism and empiricism, and the evolution of empiricism into logical empiricism in the early 20th century, and philosophy of science in the mid-20th century, and philosophy of science in practice in the late 20th century. Scientists don't care. Philosophy isn't intrinsically interesting if you're a scientist, but it can be interesting if you find a point of contact to discuss. Okay, so those are some practical suggestions. I hope that we're in a very interdisciplinary room right now. Maybe you'll get a chance to implement some of them. I just want to close with a little epilogue from the last group meeting that I had with my group before I transitioned to my current position in San Francisco. We were talking about HOMO-LUMO gaps, which is a concept in molecular orbital theory. It says there are surface electrons. Your LUMO is your lowest unoccupied, your least energetic unoccupied orbital for an electron to be in. Your HOMO is your highest occupied molecular orbital. HOMOs are always lower energy than LUMOs. It's not entirely true, but it's true for these purposes. Sorry, chemists. So we were talking about HOMO-LUMO gaps, which is the energetic gap that is exciting to a lot of electronic research in physics and chemistry. And one of the graduate students asked, are the unfilled down orbitals always there? One of the other graduate students, not me, I was a passive observer to this conversation, answered, that sounds like an epistemological issue. And that is an example of a successful use of philosophy in science. Thank you.
Okay, so a word on how the Q&A will go. If you have a question, raise your hand. I'll bring you the microphone. Flip the switch up, ask your question, and flip it down when you finish.
Science philosopher Paul Farabin said we don't understand a particular piece of science unless we know its history. Now we're sitting on 100 years of not observing the precautionary principle with heavy consequences. Doesn't that suggest that science philosophy should be sovereign? And don't you think that nanoscience ethics might at some point become very interesting?
So I heard two questions in there. One is about the role of the history of science for scientific practice, and the other is about whether or not nanoethics may be interesting someday. Is that right?
Yes.
To the history of science question, I think that it does not, in point of practical fact, tell us anything about the way that science is practiced today. We're not going to look at the scientists in the room, tell them, you don't know your history, therefore I'm now your boss. That's not how it works. I think Feyerabend had a good point that we need to understand the history of the development of ideas in science in order to better appreciate where a scientific idea comes from, what its implications might be, both for science and for society. And without understanding those ideas, we have an impoverished understanding of our science. I think that's a tool that we can use to reach out to scientists, not by saying, oh, you poor impoverished scientist, let me tell you your history so that you can do your science better, but rather by showing, here are some things that you get from understanding history. Here are practical benefits to your research or to your teaching or to the structure of your lab that I can offer you as a sort of consultant for the sciences. To the question of nanoethics, it's possible. It's possible that nanoethics will become intrinsically interesting. There are interesting questions of cases of distribution of nanomaterials. So like the case of GMO ethics, the question of whether or not nanomaterials are going to unwittingly, invisibly infiltrate our everyday existence is one that's out there. A lot of washing machines these days use silver nanoparticles for their antibacterial properties. If you bought a new washing machine in the past 3 or 4 years, you probably have nanoparticles in all of your clothes. A lot of socks that are sold these days have silver nanoparticles in them. If you didn't know that, surprise, you have nanomaterials. But the way that we answer those questions is not about the nature of the nanomaterials. It's about the transmission of novel scientific materials into society. So I think we can look to cases of that sort of transmission elsewhere in science in order to understand most of what we need to understand for nanoscale ethics.
Right here.
Yeah.
Thanks. I have a question about your inquiries into the scientific method and actually looking at lab dynamics. particularly around tacit knowledge formation or transfer. I think that's one of the more challenging aspects as you get deeper into the research sciences. How do you do that? And I'm curious if you had any insights from any of your interactions or from your survey or collaborations about how scientific intuition or tacit knowledge works in a practical way in the scientific method.
Yeah, so the idea of tacit knowledge, I mean, we, as philosophers, we think of tacit knowledge as know how versus know that, or of the kind of knowledge that you get from knowing what I don't know, knowing how to operate the transmission electron microscope rather than just tell you all of its parts and the analogies between those parts and the parts of other microscopes. So I think the biggest thing that I see is they don't call that knowledge, they call it training. They have a different vocabulary for it. And if I were to follow up on the idea of tacit knowledge in the way that some philosophers of science have, I would look to the parts of the lab experience that our graduate students call training and the mechanisms of transmission for training. So you'll often see a graduate student be assigned an undergraduate student to say, go train the undergraduate on this synthesis, go train the undergraduate on this microscope. And I would look to those areas. So I think, yeah, go ahead.
So maybe a bit of a clarification.
Yeah.
Maybe semantics, but my use of tacit knowledge is more about sort of a phenomenological understanding of something, maybe preconception.
Oh, I see.
So how does tacit knowledge eventually generate new conception
Yeah.
in scientific understanding as you're developing theory
Yeah.
as a part of the scientific method, not just on the practice of how to set up an experiment, but how do we go from, we think, we have some sense of how this works, how it comes together, and we haven't yet formulated into a theory, but we have some experience of it.
Yeah. So I haven't spent any time thinking about that transmission mechanism or about it in that way. But one thing that strikes me about that is that the chemists that I work with use a variety of different what's called characterization techniques. So, nanoparticles, I can show you that red vial. You can't see anything interesting about the structure of those materials by looking at it with your naked eye. We have to use very fancy microscopes and other sorts of instruments to understand what's going on in those materials. And the graduate students and the postdocs and the PI in the lab have very strong intuitions about which characterization method to use in which experiment. I think it'd be really interesting to follow up to see where those intuitions come from and how we could then use those to understand relationships between individual, both experiments and materials, but also between the kinds of structures and behaviors that are studied.
So you gave some really nice recommendations about, as an individual interested in collaborating, how you might do that given the way the education system works.
Yeah.
If you had the power to make curricular or systemic changes, do you have any thoughts on, like, pedagogically on that level, what would help us as universities, as centers, things like this, to be better situated for collaboration?
I feel almost like you're giving me a setup to talk about how great the Purdue lecture series is right now, because I was out to lunch with some graduate students from both philosophy and electrical engineering earlier today, and I'm looking at a room with some scientists and philosophers in it. We had a little bit of institutional infrastructure that crossed between philosophical and scientific borders in Pittsburgh. We have virtually none in my university right now, and I'm working to change that. But creating spaces where philosophers and scientists are in the same room talking about something, even if it's not their research, if it's a lecture on food ethics or a lecture on why you should care about collaboration. That's a space to start conversations. And I think the lessons that I have about how to foster collaborations can't upscale to institutional levels. I can't recommend that a department go practice conceptual analysis on another department. But I think creating spaces where there are more opportunities for that sort of engagement and more awareness of what other areas of the university are doing is going to make it a lot easier to walk across the borders. Yeah.
Hi, I have a question about your taxonomy at the beginning for the different ways that philosophy, or philosophy of science in particular, or philosophers when they turn their attention to science, would interact with science. So, one way that people think, one way of thinking about the interaction is if you take philosophy of biology, sort of the most concrete problems in philosophy of biology overlap with the most abstract problems in theoretical biology. And so there's a that kind of fits pretty well though with the continuity, with Quine's idea of there being continuity, just different levels of abstraction, but there's a place where they overlap, so it's a natural place for them to collaborate. So it's collaboration, but it's also the continuity part. Another way in which there might be collaboration would be what you mentioned about giving conceptual solutions to certain experimental problems. And that seems to fit very well with the handmaiden concept, which originally, of course, philosophy, the original idea of the handmaiden was in the medieval period when philosophy was the handmaiden of theology, and conceptual solutions to theological problems were done, and there's all sorts of interesting philosophical innovation that resulted from it. So, again, with science, it might be that this could lead to philosophical innovation, but it's a kind of handmaiden thing where you use your conceptual expertise to help with the experimental problems. So so in a way I'm fitting your collaboration under both continuity and under handmaiden. Is there then, am I missing something where you'd want to separate out? And then there's this other thing that wouldn't fit under handmaiden or continuity.
Yeah, so I think that there's an acknowledgement of difference in methodology, difference in interest, and the ability to have a collaboration that is mutually beneficial or beneficial to one party or beneficial to the other party, that is captured by the idea of collaboration. That doesn't mean that those other relationships never exist as a form of collaboration, but to acknowledge more generally that what we're trying to do in those instances is a form of collaboration, rather than genuinely saying what I'm doing as a philosopher of biology investigating, the question of the gene concept is just another form of science. There's something to calling it philosophy that dictates who you're going to talk to, how you're going to talk about it, the resources you're going to draw, and the ways that you're going to frame both the philosophical and the scientific questions that you ask, that I think you lose if you call it continuity only. In the same way, I think the conceptual solutions to experiment is a form of service work that philosophy is doing for the sciences, but I also got a lot out of it myself that isn't particularly interesting to them. The idea of surface as posing problems to traditional concepts of inter-theory relations in philosophy is something I actually tried to explain it to the graduate students in the group 2 or 3 times, and they were sort of like, yeah, but so what? This doesn't make a difference to me. It makes a huge difference to the philosophers of science. So when we think about handmaiden, you could call that a species of collaboration, and you could call the shared conceptual foundations investigations a species of collaboration. I'd be hesitant to call it a continuity approach even then, but yeah, I think I'm not suggesting that there's nothing in those previous relationships. Yeah.
Thanks. Right here. And then you.
Hello. I have several questions. It was a great talk, I thought. But I think that the main one in my mind is, I guess, as a researcher, is it intrinsic to the research endeavor to be interdisciplinary? Because you could have chosen to. And it was also kind of a historical accident, right, that you ended up in the nanoscience lab. You might have had your heart set on another kind of lab, and then, well, you were shut off from there, and then you went to this one, and I'm going to work with what I got. Yeah, so do you think that as researchers we have to go across the aisle with other disciplines or not?
As philosophical researchers?
That's right.
Okay.
Yeah.
So I think that there are ways of doing philosophy of science that are more traditional philosophical interpretation of text, critical analysis of texts, looking to both scientific papers and philosophical papers in order to answer questions about the structure of theory. I think that's an incomplete, it gives us an incomplete picture of what science is about. There are philosophers of science out there who believe that we're not looking for a complete picture. We're looking for a picture of what science could be or should be, or what the structure of scientific knowledge will look like at the end of days for science, once we've finally gotten it right. To me, that's a bad way of doing philosophy of science, and I think part of my much longer term project is to use the descriptive account of the structure of scientific practice that I get out of my collaborations with the nanoscientists in order to paint a new picture of what the structure of scientific theories is. So I don't think that one needs to collaborate actively with scientists over many years in order to do effective philosophy of science. I think if you make it through a 40 or 50-year career as a philosopher of science and you've never spoken with a scientist, you probably have either a very limited domain of research that's very specialized, or you're missing something. And I'd bet money, maybe not a lot of money because I don't have a lot of money as an assistant professor in my first year, but I'd bet some money that it's the second one. Just one quick note on the historical accident of working with nanoscientists. I was looking for other nanoscientists to collaborate with. So I worked with another lab that was doing colloidal nanosynthesis once before he told me, I don't have time for this, I'm trying to get tenure, go down the hall. And I did. So, yeah.
Okay, this will be the last one. You, right?
My first question is a personal one. How do you find it living in San Francisco on assistant professor's payroll?
Interesting.
Yeah. My more serious question. You mentioned when speaking sort of the mechanical engineers sort of eyes glazing over and stuff like that. And as scientists go, I'm one of the weird ones. I'm always interested in lots of things. I'm sort of a bit of a scatterbrain. And when I go into other departments, you find sort of in science this hierarchy. Physicists look down on chemists, chemists look down on biologists, biologists don't like ecologists, and like...
Yeah. Mathematicians look down on everyone.
Yeah.
I've seen the XKCD comic, yeah.
So I think when it comes to... I think that mentality is fairly well ingrained. Here being at this research park, I imagine it's different. I think when it comes... So those electrical engineers you were talking to, were they undergrads? Or were they...
They were graduate students.
Right.
Right?
So there's a society here at Purdue called the Polymath Society. And essentially what's done there is different lectures are put on every week by... and it could be anything. So we could have anything from synthetic biology to pop music in Soviet Russia. And... You get a very like sort of diverse audience. So you see when there's a talk on stem cells, what the ethicist will say about stem cells, and you get this sort of mixing. So you can understand other researchers, see that they're actually quite reasonable people with good ideas, and maybe when it came, someone in the back asked about sort of what you do to change sort of the infrastructure of university, maybe setting up more societies like this. Maybe you could. Maybe I imagine San Francisco State would benefit from one. Maybe that was just a suggestion from me, so yeah.
Thanks.
All right, well, thank you again.